Hello everyone, this is Karthik Essen, studying in Sri Venkateshwara College of Engineering, Computer Science Department. Today I'll be presenting a seminar on optimizing IoT traffic patterns using adaptive aggregation under the guidelines of Ms. Sureka KS, Assistant Professor, Department of CAC, Sri Venkateshwara College of Engineering, Bengaluru. So moving on to the seminar topic, optimizing IoT traffic patterns using adaptive aggregation. So let's begin. So coming to the abstract, Internet of Things drives lifestyle and smart city infrastructure due to rapid growth of services and activities and develop well-being. One of the main challenges that resulted from the exponential spread of IoT is a dense number of nodes with a huge amount of data over different networks that influence the collision probability and network congestion. Existing aggregation techniques worked to solve these challenges with overlooking the IoT traffic characteristics and their types. Here, adaptive aggregation techniques is proposed based on IoT traffic types to overcome IoT network issues. It is anticipated that the proposed adaptive aggregation results could optimize the efficiency of IoT smart city networks in most performance matrices compared to existing aggregation techniques. Internet of Things drives lifestyle and smart city, like the mentioned in the abstract. So based on this, today's topic will be an adaptive aggregation of collocation methods for the congestion and traffic using Internet of Things. So moving on, the contents on today's introduction, literature survey, methodology, conclusion and future work, and references. So these are the contents I'll be discussing on today's slides. So moving on to the introduction, IoT. Smart city network suffers from complicated IoT in traffic. This IoT traffic is not optimized, may result in low throughput, high collision probability, high network traffic, congestion, etc. So these are some of the drawbacks where using IoT is because of the IoT traffic will have low throughput and high collision rates, high network traffic and congestion. The adaptive aggregation process plays a crucial role in improving the performance of most IoT smart city. This technique shows correlation between aggregation properties on one side and the IoT traffic patterns on the other side in order to perform an adaptation process among them. Finally, there are two methods based on aggregation, that is, one is time-based aggregation and collocation-based aggregation, either of which is adopted to control data traffic in smart city networks associated with a periodic traffic pattern and payload traffic pattern respectively. So moving on to the scope of the topic on today's discussion, the two proposed aggregation techniques, collocation-based aggregation and time-based aggregation, are adopted by payload exchange traffic networks, and periodic traffic networks by sync node improve the network performance efficiency. Here the sync node plays a crucial role in the topic of adapting either of the aggregation methods. The proposed adaptive aggregation techniques could minimize the latency, reduce the collision probability for dense number of nodes, achieve less traffic congestion and reduce recurring data. The proposed adaptive aggregation techniques could minimize the latency. One is it decreases the time between the processing of the data, reduce the collision probability for dense number of nodes, achieve less traffic congestion and reduce recurring data. Literature survey. Title: on supporting IoT. Some of the literature surveys are taken here. One such literature survey is as mentioned, on supporting IoT data aggregation through programmable data planes. This is one of the literature survey by the author in the year 2018. The author's names are mentioned here. So the work done under this title is the 3 layers and connected via the UDP IP protocol. Here we are using UDP IP protocol to connect the 3 layers. The protocol is written in high level language and is intended to be implemented on switch aggregation that sends data to IoT gateway. Limitations: a traditional TCP IP protocol guarantees reliable connectivity compared to a proposed UDP IP protocol. This is the limitation for the title on supporting IoT data aggregation through programmable data planes. Second literature survey is queuing, delay analysis and optimizing the statistical data aggregation and transmission systems, given by so and so authors in 2019. Here the work done in this title is proposed a statistical data aggregation method to identify ideal aggregation to minimize the mean total system time. Here this title literature produced or proposed a statistical data aggregation method in which reduce the mean total system time. The limitation of this is experiments were conducted only at the suitable conditions, which was stationary arrival conditions, but in real time it was not practical. Moving on to the third literature survey is on global information and infrastructure and networking symposium, given by Hideki Oshio, Kinoota, Takufumi Hiraguri in year 2019. The work done here is presented the time aggregation scheme to gather data traffic, every constant inter-arrival time from one node to multiple node into the sync node, and to overcome the problem of the stationary arrival conditions. Limitations. The proposed aggregation scheme could not minimize the redundant data. This was the limitation. Sorry for that. This was the limitation on the title Global Information Infrastructure and Network Symposium. Adaptive control of non-statistical sensor data aggregation to minimize latency in IoT gateways. This is the next survey given by Hideki Oshiono and Kento Ota, Takifumi Hiraguri in year 2020. Proposed an adaptive control strategy for statistical data aggregation when the arrival rate varies over time. Varies over time. This is the work done under this title. The limitation is the adaptive control for non-statistical aggregation used three types of estimated formulas. So this was a quite bit complex, which was one of the limitation of the process. So in the literature survey, titled Traffic Aggregation Techniques for Optimizing IoT Networks. This is one of the title given by A.S. Ibrahim, K.Y. Youssef, M. Abolata in year 2020. Work done, proposed two aggregation techniques in space domain attributes, single node type, multiple node type, and time domain attributes to improve network performance in smart city use case. This is the work done, and the limitation is the proposed aggregation scheme lacked the adaptive nature of selecting between the two aggregation techniques. So the limitation of the traffic aggregation techniques for optimizing IoT networks was the proposed aggregation scheme lacked the adaptive nature of selecting either of time aggregation or collocation aggregation techniques. So this was one of the limitations. So this is about some of the literature surveys. Now the problem statement on today's topic: optimizing IoT traffic in smart city network using adaptive aggregation technique. So here we'll be discussing on adaptive aggregation technique, where how the adaptation process takes on between time aggregation and collocation aggregation method. So the methodology followed here we consider two main aggregation techniques: collocation based aggregation and time based aggregation, as discussed before. It smartly selects between two aggregation techniques by the adaptive method based upon the correlations with the characteristics of IoT smart city traffic patterns. So following the traffic patterns of IoT smart city, here we'll be selecting either of the two aggregation techniques, but the adaptive method based upon their correlations. So specifically payload exchange traffic pattern and periodic traffic pattern. Here the payload exchange traffic pattern is for collocation and periodic is for time based aggregation. So discussing on collocation based aggregation. So exactly what is collocation based aggregation? So here we'll be discussing a simple space domain aggregation, and further enhancement on space domain aggregation will explain what collocation based aggregation is exactly all about. So first discussing a space domain aggregation. Here the space domain aggregation using a simple diagram. Here you can see there are different sources wherein sending data packets, and each source has their own transducer and own processing node, which is all going through a single sync node. So here we can see the space domain aggregation. The traffic data of n source nodes are accumulated to a single sync node. So each source node has a transducer plus the processing node. Sync node aggregates a massive number of packets from n source nodes onto the sync node. Each packet is composed of control data, overrides, and the user data. In this technique, since massive number of packets sent to the source node massive number of packets are sent from the source node to the sync node, it results in a network traffic congestion. This is a simple space domain aggregation as shown in the diagram. Some further enhancement on the simple space domain aggregation gives collocation based aggregation. So here in collocation based aggregation, here it will have a single processing node, wherein in space domain aggregation we saw each transducer had their own processing node, but here a single processing node will have multiple transducer connected to it. So in this case the n source nodes add a transducer for each, but only one processing node. The processing node aggregates the packets from n transducer without applying a transmission process. So here the processing node aggregates the packets from n transducer, so multiple transducer to a single processing node. Excuse me. Sorry for that. The processing node aggregates the packets from n transducer without applying the transmission process. The processing node transfers the aggregated packets into the sink node. This technique can reduce the number of sent packets without eliminating confidential data. So this is one of the advantages of the collocation based aggregation technique, wherein the sent packets without eliminating the confidential data can be reduced. Therefore, it could be applied for the payload exchange traffic pattern that is characterized as a massive number of transmissions, continuous transmission, and a huge amount of data is sent. So when the characteristics of arriving data are so and so, stating massive number of transmission and continuous transmission and a huge amount of data, there will be a payload exchange traffic pattern which follows collocation based aggregation. So here is a workflow block diagram describing how a collocation based aggregation actually works. So here reading the block diagram, making it easier. Start, and there will be identification, processing, ordering of the data, aggregation, and there will be a for loop wherein D, that is sensed data of size D, and S, the length of the packets which is compared in the for loop, and if it is yes, it proceeds in sending, and if it is no, there will be a concatenation process, and finally it is sending and end. So it can be handled the k number of packets of a length S from n transducers. The buffer size B could be evaluated as the formula mentioned, B is equal to K into S. Each transducer generates an amount of sense data of size D. To avoid buffer overflow, maximum number of n transducers that could be attached to the same processing node should be limited to n is equal to S by D. This is the formula which will be controlling the buffer overflow. The processing node processes sensed physical parameters from n transducer. The processing node produces sub-packets that are temporarily stored in their buffer. The processing node allocates the IP packets with the gathered sub-packets. Once IP packet is fully occupied by sub-packets, the processing node immediately occupies the next IP packet in the concatenation manner until the sensed data D is exceeded. So this is the working procedure based on B is equal to K into S and N is equal to S by D, two formulas, wherein you'll be you will be proceeding the collocation process based on the packet size and length and the buffer overflow. So once the IP packet is fully occupied by sub-packets, the processing node immediately occupies the next IP packet in the concatenation manner until the sensed data D is exceeded. In this type of aggregation, processing node acts as a broker node that aggregates data S from n transducers. The processing node sends IP packets into sink node, which forwards those packets onto the higher layer. So this is the collocation based aggregation, and the block diagram representing the working method of collocation based aggregation. So moving on to the time based aggregation, here a bit complex compared to the collocation based aggregation, but here you see there is a processing node and a transducer for each of the source node. The proposed technique is aggregation of data bytes on one or multiple source nodes at TG grooming time instead of sending them one by one. After aggregation, each source node sends regularly its aggregated data bytes into sink node at the end of TG time slot. Since node can accumulate overall aggregated data bytes from several source nodes and forward them into designed cloud, It could be applied to a periodic traffic pattern that is attributed to regular transmission time, fixed interval, and small packet data transmitted. So when a characteristic of received data is fixed inter arrival time and regular transmission time, a periodic traffic pattern is applied, wherein a sync node can accumulate overall aggregated data bytes from several source nodes and forward them into a design cloud. This is the working of time-based aggregation, and here you can see the block diagram, wherein here buffering, filtering, and aggregation process is quite different compared to collocation-based aggregation. Shows a detailed description of the proposed time-based aggregation workflow. Processing node begins to organize incoming sense data from the transducer. After start, before aggregation, the sense data are buffered as a raw data stream. This is an additional process compared to collocation-based aggregation. Valuable raw data stream was chosen to remove the raw data redundancy in a filtering process. Here, a filtering process applies a raw data stream, valuable raw data stream, where it removes the data redundancy. In this method, the filtered raw data is aggregated onto the IP packets at an instant time t. The source node permits filtered raw data to occupy packet until it reaches fully capacity. D is less than or equal to S, and continues to concatenate the next packet with the next filtered raw data. It continues to aggregate data until time is greater than the grooming time, that is TG. The source node sends packets into the sync node. Here we'll be using a grooming time compared to the instant time, and for the for loop we'll be using a packet size and the packet length. And if it is yes and the instant time is greater than the grooming time, the sending is proceeded. If not, the concatenation process is occurred, and then again if the grooming time is lesser or greater than the instant time, it is pushed to aggregation. After aggregation, the process continues. So this is about time-based aggregation. Now, coming to the main method, adaptive method, wherein you will be choosing either of time or collocation aggregation method. Sync node plays a crucial role in adaptive method. Like I said before, sync node is a major node, wherein you will be choosing between two of the aggregation techniques. The source node send their packets into sync node. It extracts an assigned source IP address from the received packets. After that, the sync node recognizes the traffic type of received packets based on IoT traffic characteristics. It can inspect and extract features of incoming packets based on inter-arrival time, sent packets, packet size, and packet arrival times. After feature extraction, sync node will understand main four features, classify them into traffic patterns, and decide a suitable decision based on this classification. Now coming to the block diagram, here you see a receiving packets, that is the first step, and node identification of the nodes, and packets recognition and traffic classification, and the decision is made according to the sync node. And if the decision is yes, it moves to payload exchange. When all of the above block diagrams are satisfied and the decision made is yes, it moves to payload, and which proceeds collocation aggregation. If not, it moves to the periodic time method, and the time aggregation method is followed. When a received packet has following features, like I said before, irregular inter-arrival time and huge amount of packet size and the massive number of sent packets, it chooses payload exchange traffic pattern, and the collocation based aggregation technique is followed. On the other hand, if the features are a fixed inter-arrival time, a small amount of packet size, and a low number of sent packets, it chooses periodic traffic time, and time based aggregation is followed. Such scenario, sync node enables the source node to perform the time-based aggregation technique by sending back the acknowledged message. So here are some few experimental results, experimental graphs. When we follow classical aggregation method or the proposed collocation-based aggregation method, as mentioned before. Here the proposed collocation-based aggregation methods are mentioned in red, or described in red, and the classical aggregation methods are described in blue. Here you see first graph representing traffic volume, wherein you have sensor or transducer on x-axis and m bits transferred on y-axis. And the second graph is throughput, where you have sensor or traffic transducer on x-axis and kbps on y-axis. You can see the rates are much more higher in proposed collocation-based aggregation compared to classical aggregation. Moving on to some more graphs here, you see a number of sent packets and number of overheads wherein you'll have a sensor or transducer on x-axis for both and send packets and KB on y-axis for both. Here you can see still the proposed collocation is represented using red and classical aggregation method is represented using blue. You can see the rates are much more higher comparatively, and which is prominent that the rates are higher here in proposed collocation based aggregation, and the congestions are also reduced. Here are some pie charts representing the same as mentioned before, but you can in a different representation. You see the pie chart here, but here you have grooming time in the x-axis, the same following attributes on y-axis, m bits and kbps. You can see the transmission rates are much more higher in proposed time-based aggregation, wherein the classical time-based aggregation it is much more lesser. You see the first pie chart representing traffic volume and the second throughput. Here you see the number of sent packets and control overhead, same having grooming time on x-axis and sent packets KB on y-axis. The proposed time-based aggregations are much more higher rates. Have a look on the pie charts. You see at the grooming rates increases, transmission rate decreases, wherein both the transmission rate decreases accordingly, but proposed time-based aggregation has much more transmission rates and based on the sent packets. So coming to the conclusion on the today's presentation, adaptive aggregation based on IoT traffic characteristics have been proposed to solve the IoT critical situations at physical layer. Results verified that the two proposed aggregation techniques, collocation based aggregation and time based aggregations, are adapted on a payload exchange traffic networks, periodic traffic networks by sync node S to optimize network performance efficiency. The proposed adaptive aggregation techniques could minimize latency, reduce the collision probability, achieve less traffic congestion, and reduce recurring data. So these are the possible following advantages. Future works, the experimental setup was to optimize traffic in IoT smart city network use case. That was the original idea, but it can be extended for the other IoT use cases. So these are some of the references I took from IEEE. So that's all for today's presentation. Thank you.